All right, so here is a fun NASCAR problem, okay? So the Motor Speedway up in Bristol is known for two things. One, that it's a short track and it's very fast, fast that way. And it's also very steep, okay? And so kind of what I'd like to know here is uh, what's the fastest that a car could go around one of the turns at Bristol? Okay. So what we need to start with is just sort of the situation that we're looking at, okay? And so Bristol, it's kind of, it's not a circle. It's got these straight bits and then some curved bits to it. And the radius of curvature here, as you're going around this circle, is about 75 meters. Okay. Which is much, much smaller than most of the other racetracks on the NASCAR circuit. Okay. Um, then if we look at this thing from the side, okay, let's suppose we got our car over here somewhere on this track. We have it's banked like so. All right. And the car is sitting on there like this. Okay. And then this angle here, theta. All right. It does vary. And over the years, it's varied as they've resurfaced it different times and from when it was originally built and that sort of thing. But it's about 25 degrees right there. Okay. 25 degrees. Okay. So that's where we're going to start right there. We're going to think about our situation like this. And as this car is going around the track, the acceleration it has is this way. Okay. So we've got some radius here, some r. And so we're going to have a centripetal acceleration, which will be that v squared over r. Okay. So now let's look at what forces are acting on this thing. And so obviously there's going to be some weight here, just like this. All right. And a normal force from the track here, just like that. All right. Now, as the car is going around this bend, okay, it would like to keep going straight. And so there has to be some friction. And the friction that it encounters is actually parallel, just like that. So there's our friction. Okay. All right. So that's the only thing we got. All right. So as it goes faster and faster, we're going to have more and more friction to keep it from sliding up the embankment as it comes around. Okay. And that's going to be a static friction. All right. Even though the wheels are rolling, the wheels are not sliding. Okay. So it's not kinematic. It's static because they're rolling. All right. So now let's get to a free body diagram. Okay. And so now oftentimes on our free body diagrams, if we're on a slope, we make our free body diagram tilted. Okay. However, in this case, because of the direction of our acceleration, that's not helpful. We would end up with part of our acceleration in the y and part of it in the x, and it would just be a mess. So it's really safest in this case just to go with our ordinary setup. Okay, so this means I'm going to have my normal force is going to be here. Okay. This angle there is 25 degrees, which means this one is 65 degrees. My weight is still straight down. So there's my weight, my normal force. And then my friction is going to be at a right angle, just like this. And this angle is 25 in there. Okay, just like that. Now, what's the direction of the acceleration? It is this way. Okay. So there's no vertical acceleration. The car's not popping up from the track. It's not sinking into the track. So we don't have any vertical. We have only horizontal. And so what that means then is it means that we're going to have, I'll do this in a different color. We're going to have the horizontal component of N. So let me call that Nx. And the horizontal component of the force, Fx. Those are both contributing to the acceleration. Okay. Now, vertically, what we have going on, we're going to have an Ny here. And we're going to have an Fy down here. So you can see vertically, Ny has to balance out the weight and the downward component of the friction. Okay. Just like that. All right. So now we're ready to put some things together. Okay. All right. So let me use some yellow here. Okay. And we'll start with our X information. So Fx is Max. Okay. And so we're going to have Nx to the right. And we have Fx to the right. Okay. And that's AC. Just like that. Now Nx is going to be N times the cosine of 65. And Fx is going to be F times the cosine of 25. And so we're going to put in here mv squared over r. Okay. Now I want to substitute in, do a little bit more algebra there, because we know that the friction, okay, is always going to be less than or equal to mu times the normal force. We want to know the fastest that it can go, which means we're going to be at the max. And so we'll actually choose that the friction is equal to mu times n. Okay, so that puts us right at the very limit of what our friction can do for us. So if we plug in here, in cosine 65 plus mu in cosine 25, that's mv squared over r. Okay, one more step of algebra here. Let's pull out the n. So I have cosine 65 plus mu cosine 25, and that's still mv squared over r. Okay, there we go. Okay, so we're interested in trying to find v, and so you can see here then if we could get something about v, then we could get n, or other way around, if we could get something about n, then we could solve for v. Okay, boom. So move this a little bit. Okay, I don't want to lose track of my my free body diagram there. But what we're going to do now, we're going to look in the y direction. Okay. And so in the y direction, we're going to have ny is up minus fy minus mg. And there's no acceleration there. So that leaves me with ny minus fy has to be mg. Okay, so now I want to substitute in like I did before, okay, where I turned nx into n cosine theta, that sort of thing. So now we're going to go ny will have to go as n sine 65 minus f sine 25, and that's mg. Okay, we'll make the same substitution in for the force by saying that that's got to be mu times n. Okay, So now I've got n sine 65 minus mu n sine 25 is mg. Okay, again, one more step here. We're going to pull out the n, 65, minus mu sine 25 is mg. Okay, here we go. So then n becomes mg divided by sine 65 minus mu sine 25. Okay, so there's my expression for my normal force. Okay, now that's the maximum normal force because we're operating at the maximum value of the friction. Okay, if we weren't at our max, then we wouldn't be guaranteed that that's what n is. Okay, but we are, so it's all good. Okay, then what I want to do is I need to take that expression, and that's going in right here. Okay, that's going in right there. All right, now I'm going to skip a little bit of algebra, okay, because just for the sake of time. Okay, and let's pick a good color here. All right, so I'll stick with, let me see, what shows up pretty nice. Well, hard to say. I'll stick with white. Okay, so I end up, for n, I end up with mg. Okay, and then what I'm going to have is this cosine 65 plus mu cosine 25 over sine 65 minus mu sine 25. That is mv squared over r. Okay. Now, we never put in a weight for the car. We never put in the mass of the car. And so this is kind of cool. You can see actually the mass of the car doesn't actually matter. All right. And so then let me do a little bit more algebra here. We'll get to our final answer. And the v is actually going to be the square root of g times r, and then the square root of all this stuff. Cosine 65 plus mu cosine 25 divided by sine 65 minus mu sine 25 to the 1/2 power. Okay, so that's my expression for my velocity. All right, now if you plug in all the numbers we've got here and we up above, it says, hey, there we go. Where does it say? Here's mu is 0.95. Okay, so if you plug in mu equal to 0.95, what you end up getting for that maximum speed is 43.3 meters per second. Okay, now that's not all that fast. That's about 97 miles an hour. Okay, so when I got that answer, I was a little concerned because it seemed way too low. And so I checked and I double checked my numbers and my math and everything, and I couldn't find any mistakes. And then a couple of things occurred to me. Okay, and one thing that occurred to me was that when these cars are actually racing, let me try to draw a little bit better job here of an oval like this. The path they take, if you've ever seen the racing, they kind of go from the outside to the inside and back to the outside like that. So the actual radius of curvature is not 75 feet. It's bigger. Okay, it's bigger. And so if we had a bigger radius of curvature, then you can see that's going to affect our value for the velocity that way. Now it goes as the square root, so it's not a huge effect, but you know, if it was, you know, 16% greater, then we'd have a 4% difference, that sort of thing. Okay, so that kind of makes some sense there. Now, then I also kind of read, because I was sort of thinking NASCAR races, I was thinking these cars are going 200, 220 miles an hour. And, you know, so you can see when I got to 97, I was like, whoa, okay, that's not right. And then come to find out a couple of things. I didn't realize this. I'm not, I know this probably makes it sound like I'm a huge NASCAR fan. I'm not at all. So I didn't know this, but at Bristol, those cars only go 130, 135 miles an hour. So they're not going nearly as fast as they can on the other tracks. Okay. And this is part of that reason. All right. Okay. So that's pretty good. Now, so that means kind of the goal I want to try to get to is, you know, around 130, okay, is what I would hope my calculation would come out to. All right. Well, then I found out that the tires that they use on the NASCAR cars are very soft rubber, very soft, and they get hot. And when they get hot, they get sticky. Okay. And so it's actually maybe more realistic that mu may be as high as 1.3, okay, because the tires are actually sticky. So we have an effective coefficient of friction that's significantly higher than we thought before, okay. Now, if you take that value for 1.3, that value for mu, and you substitute it in down here, okay, then what you end up getting is a velocity of 129 miles per hour. Okay. And so I felt pretty good about that one then. We got everything to line up just right that way, but had to use more realistic values for some of those things there. Okay. Now I didn't try to factor in a different radius of curvature. I just did it, recalculated it using the coefficient of friction. Okay. So anyway, doesn't look like that much when we shrink it up there, but there it is for you. Okay. The physics of NASCAR cornering. Okay. There you go.